So yeah, welcome everybody. Today we want to talk about how to efficiently separate automotive functions within a multi-core system. So basically within one ECU. Let's have a quick look at the agenda for today. So yeah, we want to have a quick look on the motivation, the challenges the users have to handle, and the general solution, how to handle it, how a possible solution, how to handle it, the specific implementation from Electrobit with the EBTRIS's hypervisor, and also in combination with the EvoCorpus virtual Ethernet switch for the communication needs. Then we have a quick look at a short comparison between a static hypervisor, this is what we are talking here, and a dynamic hypervisor, and then a short summary. Okay, let's dive right in and have a look at the motivation. So basically, we look at these five trends, right, which come in from different directions. We have the market, where we have new vehicle architectures approaching. So we're talking about the movement to so-called zonal architecture. Yeah, here function consolidation, as also in the introduction mentioned, is a key factor. Same as the business model. Here we talk about software as a product. In the future, we think that software plays a key role in making a vehicle successful and also differentiate the market. Then efficiency, shorter development times are also a key factor in the future to shorten that, so the requirements from the OEMs get bigger and bigger to have shorter development cycles here and to deliver functionality in a faster fashion. The legacy migration, here we just go in the same direction as shorter development cycles, but with the new EE architecture, we still have the need of reuse of already developed functions from the past, and to enable those to be integrated into a new ECU. And then the last one with the development, I think this is one of the biggest ones, since software is driving also functionality in the future car. Distributed development teams are more likely to be established in the organization of the functional providers, which means that there is bigger software teams which work at different locations, and to handle the complexity of modern software development, it is necessary to have clear borders between the software in the system itself. Okay, let's look at the challenge which arise out of these motivational aspects. So one big challenge is the homologation of functions within the vehicle. So we have different development cycles for different parts within our ECU, right? Might be that there is some OBD implications, means one part of the software is relevant for OBD legislative requirements, and the other part is a pure functional non-OBD part, which need to be put together into one box. Another one I mentioned that is a big one actually, is the consolidation of functional application sets on one ECU. That means that I really have out of my legacy components, I want to consolidate multiple functions within one box to save the amount of ECUs in the car, or reduce the amount of ECUs in the car. And with this, we have the challenge how to handle those if they, for example, come from different suppliers. And the third one actually goes down the road for functional safety. Here, if I have a mixed criticality system where I have hard real-time requirements and I can basically separate those functions from each other in an architectural fashion, then it might be also a challenge to basically bring both functions into one system, which then in the end means I have basically two stacks running side by side within one box. Okay, so these are the challenges we need to look at. So what could be a possible solution, more in a generic way, is the usage of a multi-core processor where we have a separation of the builds. We have really assigned resources to a specific partition, and the cross-core communication is handled in also an abstract fashion. So yeah, this means so what we are looking at is we cluster the ECU or the microcontroller into we call them virtual ECUs. So here we have a clear assignment of the microcontroller core to a certain partition or virtual ECU, and same with all the other peripherals and resources which are available within the microcontroller. So if we, on the other hand, look on the specific solution in this case, so what we see here is an example how it could be separated. So if we do the bottom-up approach, we have a microcontroller, in this case with 5 or 6, 7 cores. And here we have a fixed assignment to a virtual ECU. Right? So in this case, virtual ECU 1 shows that we have assigned core 1 and core 2. For virtual ECU 2, we assign core 3, 4, and 5. So here we have basically a triple. And on the virtual ECU N, we would assign further cores. And an important part here is that this is a static system. So there's no dynamic assignment of memory or processor time. So that means that each virtual ECU looks like an own, in this case, AUTOSAR system in itself. So that's the reason why we see an operating system in each virtual ECU, in each partition, an own MCAL, the whole AUTOSAR basic software which is needed, a separate runtime environment, and then on top we have our application software components. So important in this case is that this is without an MMU. So here we do not change the MMU lookup tables during runtime, and the ECU sees different memory sections at different times. It is all static setup, so I need to know which memory sections are visible to my application. And basically the virtual ECU 1 and virtual ECU 2 are completely separate from each other and do not know anything about each other, so that they need to basically handle the communication between both in a fashion as it would be existing in an own box, so that we have two separate ECUs technically. That brings in the question: how do the virtual ECUs communicate between each other? And here our approach is that we have actually a virtual communication path with a Ethernet stack on top established. So what we see here in on the virtual ECU1, which is here as a communication master, basically which provides the virtual ECU Ethernet switch. And so basically what we build up within this one system, we build up a small Ethernet cluster to communicate from an application to another application. So from an integration standpoint, for this application part on top, looks like it calls an RTE, write signal, read signal, and from there on, the communication started. If it's signal-based, right? If it's service-based communication, of course, would be also working in the same way. Here, you're also the possibility of the usage of service discovery and some IP is absolutely no problem. So since we are working here within an out-of-source system. So that means we have a virtual Ethernet driver integrated, so some sort of special MCAL in each virtual ECU. And this virtual Ethernet driver is connected to the virtual Ethernet switch, which runs on the host system, basically. And then here underneath the virtual switch, we have a physical Ethernet driver connected, which then indeed is connected to the outside world. And then there I have my peer-to-peer connection as I would expect it. So I connect to a real switch and then have a connection to the real world outside of my system. So each application would see or would be able to communicate to the outside over Ethernet and also exchange information internally through this Ethernet channel. Okay, so if we have a look at the general features we have within our virtual Ethernet switch, here we have the general features are transmission reception from all different parts of what I just said within our system, all virtual ECUs. Also support of the quality of service for TX and RX messages, same as the time sync features. So we could also provide a global time through this Ethernet channel. On the performance side, here it's clear, right? Since this is all virtual in quotes, this is actually shared memory. What is behind all of that implementation. So in this case, we can do an optimized communication on the data path between the virtual ECUs. So there is a possibility of zero copy operations where we just switch pointers basically, and also have an optimization on the lock time because we have actually a bottleneck within that one physical unit which is available to communicate. We have also a deterministic transmit and receive delay within the system due to the fact that we can exactly have a FIFO basically and know that the delay is always the same thing for all messages. So on the safety side, here we do also have the possibility of a freedom from interference argumentation on all three domains. So timing execution. So here we have basically the possibility to supervise the virtual Ethernet switch within our system by using a watchdog stack basically, which is provided from Electrobit as well. We can address the spatial domain with memory. So here I can actually separate the shared memory from each other and can guarantee freedom from interference on these message buffers within the virtual Ethernet switch. And on the communication path, of course, it is possible to use an end-to-end protection on a higher level. Actually, on the RTE layer, we would introduce the E2E functionality for communication. By the way, there is also a webinar available from Electrobit from last year where actually I'm talking about these topics. So if you are interested in that, please check that out. And then the last point, support for coexistence with safety-related components. So this is going along the way that we have a freedom from interference also on memory, so that the virtual Ethernet switch is not interfering with any other component in the system. Okay, so if we look at the features of the hypervisor, we have, so first of all, the most important, and that is what it is actually, since we don't have any dynamic assignment of core specific execution, so it's all static and predefined. We have actually a core separation. So some might argue that this is not a hypervisor in this case because there's no virtualization, but it means in this case we have actually a separation between multiple systems which are separated from each other, so it depends on the definition you're taking for hypervisor. So the core separation is actually the key mechanism of the embedded hypervisor. So what it offers is the definition for the virtual ECUs, so the partitioning, which core and which resources are assigned to which virtual ECU. Then it is basically containing individual code, means that the binary is 100% separated between the different virtual ECUs. It offers, we talked about that, the separation of OBD and non-OBD functionalities within virtual ECUs. So this is a concept for homologation. Usually the timeline for the OBD features is a bit more difficult, since there is legislative parties involved to get approval on release of certain software parts. And with the embedded hypervisor, we think that it is a valid argumentation that there is no interference between those two ECUs, so it can be released and not be touched, while the non-OBD part might be still changed in one or the other way. Then for safety, we talked about that as well. So it is possible to use an safety OS with an ASIL-D or whatever ASIL implication, and on the other ECU we run a normal EB Autocore OS, which has a QM level, and execute them in the same ECU, but on different cores, and guarantee a freedom from interference on that core level, that we are not executing accidentally commands from the other the other core. And okay, then we have a static configuration of memory regions, which means that it is statically configured which memory section belongs to which virtual ECU. So this is something I need to do upfront during my development, and this stays the same throughout the life cycle. Booting separate OS instances, I think this is clear, so I can do mixed systems, running an autocore OS, basically plain Autos OS or microkernel OS. So there is actually nothing special within the operating system. One important part, and this is also technically a difficult one to achieve, is the configuration of the interrupts. So if I have certain general purpose interrupts or interrupts coming from whatever peripheral, they can be assigned to a certain virtual ECU setup. Means that if I have a CAN interrupt, for example, is assigned to a certain virtual ECU, and then needs to be handled within this ECU and executed the service routine in there. So this is the core separation part, which is the actual, let's say, functionality of the embedded hypervisor. The big advantage here is that there is, from a boot time perspective, there's no additional add-on time for the embedded hypervisor, since this is a setup which needs to be done anyways. So the mechanisms, so what we'll look at that in a moment on the specific implementation for the Oryx platform, but here the setup of crossbars and timers need to be done anyhow. Okay, then if we look at the inter-virtual ECU communication, so as the standard approach, I would recommend using the virtual Ethernet switch, but the embedded hypervisor also provides the possibility to implement a project-specific possibility to communicate between both virtual ECUs. Means that it comes with a library to implement static communication channels through shared memory. So second point, communication via shared memory. And also OS-independent intercore locks. So that means I can, on this shared memory, have a sort of semaphore implemented. So I have exclusive access to this piece of memory in the case I do not write in an atomic fashion. So I can take a lock on this one to prevent any data corruption within the communication between both the virtual ECUs. The other part is, since we talk about inter-core communication within one virtual ECU, right? Here, it is also necessary to have some mechanisms provided to the OS. Actually, in a normal AUTOSAR system, if I would have really like the classic approach, I have a single application setup on my ECU. I have a multi-core ECU, and I do have cross-core calls. I use cross-core interrupt triggering call-outs, so the RTE has certain features for shared memory or inter-core communication. And actually the same mechanisms are still available also within one virtual ECU. So I have inter-core communication if I have a virtual ECU which is set up as a multi-core system. Okay, then safety, I cannot stress that enough. So for the freedom from interference between separate domains using hardware separation mechanism, I have a register protection, memory protection, certain peripherals, and I can, for my code execution on the cores. So they are still available. Of course, I can use the mechanisms of the specific microcontroller which are available. Then, so support of the coexistence of the safety-related components means that I have the separation between the virtual ECUs. I mentioned that before. So there is no interference between the different virtual partitions I set up. And then, further OS support. So, of course, I can execute multiple instances of the safety OS, also the AutoCore OS, on different virtual ECUs. So, for the safety OS is more important because I can, if I have within one virtual ECU, I'm executing multiple instances of the safety OS within one virtual ECU. This is also possible. And I can configure the number of CPU cores within my virtual ECU setup. Okay, now if we look at the integration, what we have done or are doing right now. So our lead platform for the integration of the hypervisor platform is the Infineon Oryx TC39X. I'm not sure which derivative exactly, but important is the usage of the core-specific memory protection unit, which is available on the Oryx. This gives me the opportunity that, so if you look at the Oryx setup, each core has a dedicated set of memory which can be accessed faster, and all the other memory blocks are connected via a crossbar and have some more delay to access, but is still accessible. And the core-specific MPU is not the normal memory protection unit. It is really like a small unit within each core, and it actually handles the communication on the crossbar of these cores. So I can physically prevent the cores from accessing memory which is not intended. And this is exactly the mechanism we make use of to implement this embedded hypervisor. So we restrict the access to the memory of the other cores. Also, the interrupt controller is an important part. Right here, I have an interrupt controller which needs to handle the interrupts in a core-specific fashion. So this one is also important for the implementation. The core-specific timers, of course, since if I would have a system-wide timer, I would need to basically take care of this for each virtual ECU in the same fashion, so that each OS which is running in the virtual ECU is set up in the correct way. With the core-specific timers, I do not need to care as much, right? I need to keep it consistent within one partition. Shared and private memory, actually I think it's clear. Here we have also sections which can be accessed by both virtual ECUs, and then they are mapped in the correct way in the MPU settings. Then the fast intercore communication, here we do make use of a special mechanism within the Oryx, and the intercore locking mechanism, which is also available on the Oryx to provide certain features of the embedded hypervisor and also to align the startup of the system. So actually there is a synchronized startup within the ECU, and so that all partitions or all virtual ECUs start at the same time. Okay, then actually a quick comparison between the static hypervisor, what we are talking about in this case, and the dynamic hypervisor, which Electrobit also offers within the EB Corvus product line. Here we have the EB Corvus hypervisor, which is actually a dynamic hypervisor which runs on high performance ECUs and micro, or not microcontrollers, system on a chip and microprocessors. Okay, so if we have a look at the static hypervisor, and we are capable of still providing a hard real-time requirement. So if you have, I mean, right, real-time capability is a difficult definition, but you would get the same performance out with the static hypervisor as it would be a normal AUTOSAR integration. We make use of the MPU instead of an MMU. There is actually not as much virtualization, so the thing which is really virtual is the communication, and actually this is not handled within the embedded hypervisor. It is more handled as a separate component. And actually, if there is the need for usage of other peripherals, like let's say a security enhancement, right, an HSM or a CAN or something which needs to be shared between virtual ECUs. It depends on the support within the hardware. So if there is a separation possible within hardware, that I have multiple CAN controllers, for example, I could assign those to the ECUs. Of course, that would need to be supported by the respective MCAL modules. And then, we have less to no processor overhead within the static hypervisor. So basically, the hypervisor is just, in quotes, startup code. So it sets the system up in a way that the operating system within the virtual ECUs, so I have two binaries basically, run as they would only see the assigned course, and they don't know anything about the other system. So during the startup time, I need to do the normal initialization anyways, so I don't lose any time. And there is no active component running in the background and doing scheduling or something like that within the static hypervisor. Compared to the dynamic hypervisor, right here, I have full virtualization of my hardware resources, especially the cores and the memory. So there I have, large operating systems like Linux or QNX running in a partition, and they see basically a dynamic system as they would expect, and they get assigned their calculation time on the processors based on configuration and availability. One key concept for the dynamic hypervisor is the usage of the MMU. So each processor can, or each process, let's say that way, each process has its own memory space, starting from 0 up to whatever is available, and that way it only sees what it is supposed to see. The overhead due to the dynamic allocation, here I have to pay a penalty basically for this dynamic approach, but usually it's used on systems which do have enough calculation power to deal with that. And of course, the usage of dynamic operating systems like Linux and QNX, which might be more problematic on the static hypervisor. Okay, and that actually brings us already to the end of today's webinar. So a quick summary. So the embedded hypervisor contributes towards the reduction of ECUs within the vehicle from its concept of functional consolidation within one box. So I have only one box and can have represented multiple functional features within the car. I could argue legal separation of the software components in terms of the homologation of OBD, non-OBD, or even safety. And I get some sort of flexibility with the peripherals, but here I have a fixed assignment, so that needs to be handled with care. The embedded hypervisor allows actually a smooth inter-core communication, also inter-ECU communication, in that case between the borders of virtual ECUs. I have the real-time behavior still as it was before, so there's no penalty on that end. I have the high hardware utilization, so I'm directly, I don't have much or more abstraction layers put into my system as I already have with the AUTOSAR architecture. I could argue with the low power consumption. This is based on the microcontroller I'm using. And then exchange of software on a virtual ECU. So basically I could also enable new bootloading concepts by only switching out certain parts, or actually one virtual ECU in a bootloading download flash loading download process. So here I get some extra time and possibility to separate those. Okay, and actually with that, I end my presentation and hand the word over for the Q&A to Martin.